Welcome back to the second session. Shall I start now, ma'am? Our guest is Dr. Praveen Raj sir. Dr. Praveen Raj sir is currently carrying out his postdoctoral research in the data acquisition and characterization of microfluidic devices at Department of Instrumentation and Control Engineering, National Institute of Technology, Trichy. He received his BE degree in Electronics and Instrumentation Engineering from Faculty of Engineering and Technology, Annamalai University. He has done his MTech in Digital Electronics from Ramta College of Engineering and Technology, Chhattisgarh. He received his doctoral degree from his work on lattice modeling and characterization of microfluidic devices at Center for VLSI and Nanotechnology, Visvesvaraya National Institute of Technology, Nagpur. He is specialized in droplet manipulation. He has Science Index journal publications and 5 Scopus indexed articles. We welcome you, sir. You can start your presentation now.
Thank you. Thank you for the introduction. Shall I start?
Yeah, you can start now, Praveen. You share your screen.
So I thank Faculty of Engineering and Technology, Annam University, especially Professor Joseph Daniel for introducing me to the MEMS technology back in 2009. So I started my research on MEMS as from during my BTech project in the MEMS lab of Department of Instrumentation. From there, I started my research. So I thank Professor Joseph Daniel for introducing me to the MEMS during that time. I also thank Professor Kavita for calling me as a resource person for this talk. So I welcome you all for this talk. So in this lecture, I will talk about certain surface issues
Hello,
in MEMS.
Praveen. Sorry, Praveen.
Yes, ma'am.
Praveen, just unmute your video.
Sorry, ma'am.
Unmute your video.
Oh, sorry, ma'am. Actually, I have issue with my camera.
Oh, okay.
Sorry. Maybe I will come in video after some times with my mobile.
Okay. Please be loudly, just a little bit, just loudly.
Okay.
Your voice is not that much audible.
Okay. Yeah. So in this lecture, I will talk about surface issues in MEMS. So right now, I am working as a postdoctoral fellow in National Institute of Technology, Tiruchirappalli. So here also, I am continuing my research on microfluidics and MEMS. So here I am using the characterization more on the characterization side than the design and fabrication. But I will present some of the results which I have done previously. So I will introduce you to the surface characterization and various technologies in handling the surface issues. Okay. So this is my content. So first we'll see some introduction about the MEMS, about the technology, the evolution of the technology. Then we'll see about the currently use micro or nano fabrication techniques and tools. Then we will go somewhat study about the nano tribology, micro or nano tribology, how to characterize the surface and all. And then we will see particularly about the surface roughness and surface wetting. Then I will present some of the case studies we encountered. Then we end up with the conclusion. Yeah, so we know about the MEMS, the evaluation of the MEMS, right? So it is a micro electromechanical system. So we have to start with this, first device which we got it in the macro scale. That was the electrostatic motor developed by the great Benjamin Franklin and Andrew Gordon. So it was way back in 1750. From there, the coupling of this electronics or the electrical domain and the mechanical domain has started, right? So from there we have this coupling between these two domains, and we have seen the tremendous scope of utilization of this technology. So then 1924, the greatest discovery, that silicon was done. Then we saw the evaluation of this IC integrated circuit, their fabrication, their utilization has become popular. Then 1954, the noticeable discovery was that piezo-resistive effect. So that was discovered by the C.S. Smith. And then we saw the evaluation of the strain gauge with the help of this piezo-resistive effect. Then we used them as a pressure sensor. Then we started about the surface micro machining with the need for this resonant gate transistor. And then we started discussion. We started the many devices have come up, like accelerometer, pressure sensor, all these things were there. In 1980, noticeably, this silicon as a mechanical material was the light was shown as a mechanical material. So up to that, it was only considered as a semiconductor, and it is mainly utilized for this integrated circuit development. But then after 1980, the utilization of silicon for the mechanical use was popularized, and from there this MEMS got the boom, and we started developing many devices like accelerometer and pressure sensor, and these keep on evolving. So right now, what we are talking about, or we are in the era of this RF MEMS, right? So we have this many MEMS devices. We carry MEMS devices every day. We carry millions of transistors with us, and also we take this antennas, inductors. They all are there with us, right? In our mobile phone, we use them. So but we are not paying attention that how many transistors we are carrying, how many antennas we are carrying, right? So oscillators, so many things are there along with us, so it is also moving with us, right? So RF MEMS has picked up, and it has gone to the next level. And we have this static devices like inductors or antennas. And much more improvement was done. If the thin film bulk acoustic resonators were developed to utilize these acoustic vibrations. And then resonators, oscillators, filters are designed to achieve the better Q without any noise or without any interference, right? We are able to achieve it, right? And many fast switches are there, switching between one antennas on one radio to other one, right? And also the tunable capacitors are developed, right? So this is the much more improvement we got recent days. And then we also have some improvement in this point of care diagnostics, like MEMS have moved from this electronic domain to the biomedical domain, and food industry, pharmaceutical industries, right? It has moved along. So now we are utilizing this MEMS device with this point of care applications, and many implantable pumps are there. With the help of this 3D printing, many things were implanted in our body, in our as a removable wearable devices and technologies have come up. And DNA chips are continuously evolving, right? So for new drug discovery and to antibacterial development, so we all are depending heavily on these microfluidic technologies with this evaluation of this DNA chip. Yeah, this is what happened. What was exactly what was predicted no long back, around 20 years back. It was a prediction that 1900 to 1950, the vacuum tube technology it was developed. And then we got, as a result of this technology, we got these devices like radio, television, radar. Then 1950 to 2000, and some early 2000, so we have this technology, that is semiconductor technology, which was dominating. And we got this evaluation of the cell phones and laptops, computers. So many computing power have evolved. And then now we are after 2000, we see that no next era, that is nanotechnology era. So in this era we are more focused on this wearable IoT applications and direct control of organic molecules, and we are moving towards the automation of these nano robots, right? So and in the mid of this era, so we are able to sense something, right? We are able to sense the utilization of these wearable technologies, and the more attention was given to this, direct control of these organic molecules, all these things. Because in fact, that Nobel prizes are being given to these technologies, those scientists which are contributed heavily on this, molecular chain reaction, control of this molecular robotics. So those focus means the need was identified in that region, and we are moving towards that way. Yeah, right now what we can see here in the MEMS, MEMS can do many things, right? Like it can hear, it can talk, right? It can feel with the help of this kind of sensor, and it can also move with the help of these actuators which was developed, uh, and it can walk, it can fly, it can grab the things which is very minute, right? Micro tweezers are developed, and it also can act intelligently with the help of this, micro computing power, or nano computing powers have incorporated along with this sensor. It can sense, of course, right? It can see with the help of this optical MEMS technology, and it can control with the help of this micro pump or a micro valve, right? Many other way of controlling is also being done, and it can synthesize, right? Micro reactors have been developed, and where we put the fluid and we get the particles, nanoparticles, microparticles with the required shape and required dimension. Those things are also being synthesized, and we can align it perfectly, right? And also we can do this cutting and much more, much more than what we have put here. So MEMS have the technology itself it's matured enough now. It can do multiple things what we humans can do it, but they can do it even in the micro scale. So that is the advantage. Yeah. So why are we focusing more on this MEMS is that no, it is having highest utility. So as per this Edison statement, right? So we want to focus our research, we want to focus our energy, and put our energy on the things which is highly utilized, right? And which has the more success, and with the help of this utility. So with that trend, what we can see economically also, right? So from the 2018 to this 2024 prediction, so the area, of course, MEMS is increasing grow. We can see that the market value of this overall MEMS devices have been increased. And more focusedly, if you look into that, some of the devices are having the constant market output, like pressure sensor, microphones, right? And accelerometers, they are somewhat stabilized, and they are the requirement of them is no reach that stability level. But the new technologies like microfluidics and RF MEMS, so the revenue generated by them are expected to be are literally are higher than that, right? And it is keep on increasing. So even the no the our research on MEMS is good, and in fact in the MEMS we have to focus on the area which is booming, right? So some of these areas are there, and it is in the commercialization, successfully commercialized. So research is not much done there, only utilization is there. But whereas in this area, like RF MEMS and microfluidics and other this thermopiles, so that research is, there is much scope in the research. Yeah, so in this talk, as I told, that we will discuss about the surface issues in the MEMS, right? So way back in the in the previous era, so the much attention was already given on the surface engineering. For example, this famous Richard Feynman lecture, right? So he talked about this, plenty of room at the bottom. So eventually he said that we need to scale down further, so that we can accommodate many and many transistors, right? So when you say the scale down, so we are creating more space, right? We are utilizing the more surface, right? We are more relying on the surface, right? So that is what he means. So when we scale down, or when we do this miniaturization, so obviously we end up with one surface only, right? We are not focused on the volume, rather than we focused on the surface. And in fact, in the nature also we see that some of these phenomenon are interesting, like these water striders. So they have these hydrophobic legs, so which means their legs, they cannot get wet. So even though it is having the mass, right, which is slightly more, right, it is that mass is sufficient to no to drown this strider. But then because of this this leg which is hydrophobic in nature, it is allowing this to fly over the water without drowning. So it is not drowning because of the leg, right, the nature of this leg, which gives the hydrophobic surface. So the surface area of this leg, which was studied and which was understood that because of this pillar structure or the hydrophobic structure of this leg, so it is supporting, it is carrying this weight in a efficient way, so that it is not allowing this water strider to drown. So the surface here, the surface which was there on the leg, which make this water strider to literally cannot wet over the surface. So, and similarly you can also see the water droplet on this lotus leaf, which is also showing some interesting characteristic, that it will not allow the water to spread over the leaf, whereas it will remain as a droplet. It will not spread over the surface of this lotus leaf. So people also studied and investigated in the microscopic level. They found that this leaf has some genuine hydrophobic structures, right? So because of this nano pillar, this surface area has been manipulated, and because of this surface area has changed, then surface energy is changed, and because of the surface energy, this droplet is not wetting, right? So that is what we saw. So what we see here, the surface level, there are much interesting science is there, and much interesting applications also waiting for us. And similarly, recently we also see listen from this this famous scientist Mandelbrot, where he talk about this roughness, right? So the obviously if you take any surface, so obviously there will be a roughness, right? We cannot deny roughness level at any point, right? Even though we consider the smoothest surface, right? If you look into the microscope or nanoscale, there would be some kind of roughness will be there, right? Only the level of the roughness may be different, but we cannot deny that presence of the roughness. And because of that roughness only, here also this droplet is getting changing differently, and because of the rough surfaces in a tuned manner, so this water strider is able to fly. Yeah, so when we do this miniaturization, so we move from the macro scale to the micro scale, right? So when we move in the typically in the it is visible to our eyes, right? So we can see the that known integrated circuit or the ship we can see, but inside this ship we can see many things, like when we scale down to the 100 micrometer to around this range, we can see the micro channel or the micro wire, right? The contact pad, all these things are visible. And then when we scale down to the 10 micrometer scale, so we are able to see the cells, right? Obviously our body cells and bacteria, right? And they can be visible below 10 micrometers. And then when we move further from 1 micrometer, below 1 micrometer, we can see the nature of the DNA, right, with the extended microscope. So we can see the radius of the DNAs, that spiral rings and all. So we are able to see, right? And then when we move further, right, when we scale it down to this molecular size, so we can see this colloid as a and polymer molecular size, right? And so the atoms, they present as a molecules, so they are also visible. And at 1 nanometer we are able to see the protein molecules. So if you want to have the control over the protein, right, our microchips or the lab on chip, what we call, so that chip is of 1 millimeter, but we want to focus on the protein in that chip, that is 1 nanometer. So nearly there are no tens of scales are difference, right? So 7 times or 8 times the scale would vary. So it is very difficult to have that instrument which can also give you the macroscopic data as well as microscopic data. So obviously the current microscope will help you to go up to certain level, right? But if you want further magnification, then we need to focus on the nano dimension, right? The question is that from where we'll start, whether should we start from the macroscopic to the nanometer scale, or from the nanometer scale to the micrometer scale. So both the way is possible, right? It depends on our dimension, our feature size. So if we are somewhat near micro scale, then we can move from the to the micro scale. But we are more interested in the nano scale, then better we start from this nano scale building block. So this is the bottom to top approach, and this is the top to bottom approach. So, and we also heavily dependent on this computers, right? So computing resources to handle this study. So and see, suppose from our computer, we are creating a number of arrays, and we are storing the data, and memory cells are there. So if you compute in the in the macro scale, which is right? And obviously you will store more and more information, right? If you store more and more information, you need more memory. Whereas in the nanoscale, if you do the computing in the nanoscale, then you may not require that many space, right? But that many space, so you the number of cells you required is less, then you can easily compute it with less memory, right? But once you but here the whether you are able to solve the solution what you get, the output of that output of the problem, if you are satisfied with this nanoscale only, then it is fine. You do this molecular dynamics or the ab initio calculations, right? So that is sufficient for you. But if you want a solution in the macroscopic domain, for example, you want to say the force in the unit of Newton per meter, right? And also you want to say some fluidic properties in the form of Reynolds number or something else, then you have to use this continuum mechanics, right? So if it depends on our output. So if we are satisfied with this nanoscale, then you can end up, or you can finish up with this micro or molecular dynamics solution tool. But if you are going for that, your output should be in the macro scale, which is convenient for the reader to understand, or convenient for us to interpret, then you need to load this macroscopic simulation. So this mesoscopic tools like this kinetic gases simulation, so they are having some kind of interface, some kind of connectivity. They provide some kind of connectivity between the microscopic scale to the macroscopic scale. So when you do the simulation in the MEMS, right? So what we need to understand is on which scale or which domain we are working on. So are we in the microscope? Are we interested in seeing the property in the macroscopic level, or are we interested in the microscopic level, or cell by cell or atom by atom we want to see? So based on that choice, we need to choose whether we want to use this FEM simulations. Obviously, most of this FEM will work with the macroscopic and some kind of mesoscopic, right? If you go to the microscopic or atomistic simulation, then your FEM may not work. Then we need to go for this ab initio or molecular dynamic simulations. So one thing also we need to notice. So when we go to this molecular dynamic simulation, we use solve more and more details, right? More and more details, because much data are not available. So here some approximations also not available. Whereas in the macroscopic level, many approximations are there. Many linearity means conversion to the linear form or convenient form is easier. So and the computation resource is less. Okay, so when we do the scale down, right, so the surface to volume ratio become critical. So for example, we take this cube and we divide into the 3 slices, right? So 1, 2, 3, 3 rows by 3 columns. So obviously the surface of this structure is nothing but is computed with the 6 different faces are there. So this 3 square into 6 is 54. Whereas the volume is nothing but obviously you need to take the cubic volume. So cubic volume is nothing but 27. So surface to volume ratio is 20, is just a 2, right? But when you scale it down instead of 3 cross 3, you scale it down to 2 cross 2. So when you do this 2 cross 2 scaling, you have the surface of 2 square into 6 faces, that is 24, and volume is cubic volume, then it is 3, and obviously your surface to volume volume ratio is 3, and you can see that there is a noticeable increase in the surface to volume ratio. But when you scale it down further, just to keep only one portion, right, then we have this surface to volume ratio is highly increased, that is 6. So that is the reason you see that sugars, right, when we dissolve the sugar in the macroscopic no scale, so it is difficult for us to dissolve it in the water. Whereas if you powder it, right, and you break them into different particles, right, minute particles, then obviously that it will dissolve quicker, faster, because it is having much more surface area, right. When you have this much more surface area, the diffusion is easy, right. But if your surface to volume ratio is less, or your volume is more, then the diffusion is difficult. So in the microfluidics, we have to understand that uh, if your surface is more, then it is easy for us to diffuse. But if your volume is large, then it is difficult for us to implement the diffusion. So when you scale down to the micro scale, this kind of physics changes are there. So we need to understand that physics change, and surface force become dominant, right. And one more thing what we can appreciate here, or we can understand here, is that when we scale down to this micro scale or nano scale, then the surface forces and surface issues are dominant than the other issues, right. So the force what we consider in the macro scale is gravity force, right, and the inertial force, viscosity force. They all are no dominant with respect to different domain, right. Whereas if you go to the minor surface or nano scale, the dominant force there is the surface force, right. So whatever we have, that surface energy is higher, right. So that surface force will make our device to work differently, right. So some can say this as a disadvantage, some can see it as an advantage. So if you look into that positive note, you consider it as an advantage, where for example we miniaturize the devices, right. So when we do this miniaturization, we need power to pump, right. So we need some energy should be there for the device to be operated smoothly. But from where we get the energy, right. So we cannot put the large inductance or large no very different sources of energy, right. Obviously it is not possible to incorporate the various sources of energy in the micro scale. But what we can do is we can tune the surface to utilize the energy, to get the energy from the surface, because the surface force is dominant in the micro scale. So if you work on the surface, then we are able to provide the energy to the uh, applications, right. So that is the idea. So that in the positive note, we can consider that surface, we can utilize the surface to its maximum to harvest the energy from that surface. So we come to the MEMS. So we use different technology for fabricating the MEMS, right. Surface micro machining is one thing, then bulk micro machining, Liga process, mold patterning, 3D printing, right. Whereas there are many various ways. So it is not that one technology we follow for every application, right. So depending on our need and requirement, we move to the surface micro machining or bulk micro machining, right. So various technology we adopt, and the technology we adopt also would create different surfaces and different surface finishes. So that finishes, the different surface finish would give us the different value of the roughness, different value of this wettability, right. And it will also start to dominate, right, various surface forces. uh, yeah, this is how we do the surface micro machining. We know that in the basic course, like we this is basically the additive process. We don't do much about the substrate. The substrate will remain as it is. We place the sacrificial layer and we deposit as per our requirement some component. Like here in this case, we want to fabricate this micro cantilever, so we place this anchor like this, and after deposition of this anchor layer, then we remove this sacrificial layer. then we have this substrate and we have this cantilever which is there on the top of this surface. So this kind of device micro machining is the surface micro machining. And obviously we have this kind of devices like micro motor, this COM drive. They are developed with the help of this surface micro machining, and it is having more number of lithography steps, but it will also provide the low aspect ratio, means you cannot go much deeper into the surface. So you have this very low aspect ratio. uh, Another thing is that about the bulk micro machining. So based on the orientation of this surface, right, again we are also here also we are using the bulk micro machining is depending on the surface orientation. So the surface orientation of the surface, you use different chemical and at different rate of this chemical, and we do this etching. So we have this V groove, we can have this, this kind of windows can be opened up, and this kind of pressure port can be developed, and membrane can be placed. So these devices are done on the substrate itself, right? And you just dig the surface with the help of this etching, and you generate this structure. So this is the bulk micro machining technique, and we the pressure sensor and this digital mirror. So it is developed based on this bulk micro machining. Then the third one, or the different thing, is that Liga process. It is the German based technology where we create the large aspect ratio devices. For example, these pillars having less surface and large height, right? So this kind of the deep structure can be generated with the help of Liga process. And in the Liga process we use the X-ray process, right? So it depends on the X-ray radiation. So whereas in the bulk micro machining and other micro machining technique, surface micro machining technique, we use only the UV lithography or electron beam lithography. But here we have to use this X-ray lithography, and we create the mold, and from the mold we can create the uh, reverse. So this mold can be reutilized anytime. So that is the advantage. Yeah, so I will just focus some attention on this fabrication technique, because how our surfaces are getting damaged, or how it can be avoided, and that can be understood only if you know this process, right? So this UV lithography process, what we do is we place the silicon substrate and we deposit this oxide or nitrate layer, and we do the spin coating of this photoresist. Then we do the soft bake. We place that device, coated device, on the hot plate, and we do this temperature treatment. We apply them, and then we align the mask, and we expose that to the UV light, right? And then we develop that in the UV developer solution, and we do the hard bake after that developer. Then we stop this lithography. So this is the process. Like we do this oxidation, and we do this photoresist, and we apply this UV light, right? So there are various process. Like we have this oxidation. So this oxidation would create some humidity over the surface, right? And similarly we have this light exposure. It may also create some defect, right? An optical property of the surface, some black dot or white, something will also will be introduced into the surface. And we also apply this temperature treatment, which will obviously modify the molecular layer, right? That will etch the, again we use some chemical for etching, like hydrofluoric acid and plasma for wet etching, dry etching. So we do this etching. So this obviously this etching chemical will also create some kind of damage to the surface. So here we see the defect here. This is the defect, right? So we need we are supposed to get the structure like B, right? The figure B, there is a step. But because of this poor defect, we have this narrow structure, and it is not useful. And similarly the trenches we should get uniform like this. And because of this uh, non-uniformity of this etching, or non-uniformity of or misalignment of this photo mask, so instead of getting the smooth surface, so we get some kind of bump here, and we get some kind of this cornered surfaces. right? So this process, UV lithography process itself would create this kind of defect, right? And it will also damage our surface. And similarly, obviously, in the oxidation process, we pass this this vapor, oxidation vapor and H2O, water vapor is there, and it will also deposit over the surface, which will also create some kind of humid environment is there, and it will attract some molecules, and it will no the water vapor will present over the surface, and also it will create some damage. Other processes are also there, like plasma enhanced vapor process, deposition process, where we use this resistant heater. Heating environment is again is there, and then you pass the gas, right? When you pass the gas, there will be some kind of gases which is conductive, or which may not be conductive also. But conductive layers, conductive gases will create will introduce some trap, charge trap over the surface. So whenever the charge is trapped on the surface or in the oxide, then that will create some defect, and it will create it will start conducting. And so for example, in a capacitor, it will create some leakage, right? So that kind of devices would create due to the surface debris. And then we have this physical deposition process. This is sputtering process, and it is cold temperature process, and you apply this electron beam, and you have this wafer. um, it will this atom by atom, the from the target material, the atom by atom, that material will be removed, and it will be placed, deposited over the surfaces. And that the uniformity would be maintained if you rotate that, right? You need to rotate that target. So, and it depends on the how uniformly we rotate, what RPM we use, right? So that is the challenge. So some places you may have higher conductivity, some places we may not have this higher conductivity. So that is the challenge in the physical vapor deposition. And obviously we have very thin layer, we get some 5 micrometer or few nanometer of the metal deposition. So when we do the measurement itself, it will damage, right? So, and some of this layer will be removed. And also this ion milling and plasma etching, reactive ion etching, right? It will also etch the molecules not a smooth way. Some places it will take, some places it may not take, right? So this molecules is not is damaged permanently. So some ions also would be removed from that molecules in this process of etching. So it will also create some debris. So obviously, because of these processes, our surfaces will have this roughness. That is what I want to convey, that the process, the lithography or MEMS process tools we are using, they will damage our surface, and it will also create some debris. And this bonding technique also, like we attach the glass with the silicon with the help of some large voltage, right? Anodic bonding. So the if some gases or some air is trapped in between, then there will be a interface issues, right? The force, the interface forces, what we expect, it is not uniform, right? So then the bonding will not take place properly. So the surface has to be cleaned properly, and it will be smooth. So if it is not, then that bonding will not take place, and there will be a air trap between them, and it will not serve our purpose. So many not only this UV lithography or the X-ray lithography, so many other techniques also coming up, right? And they are made based on this micro molding, based on this 3D printing, and based on this the PCB technology. So many assembly also there, right? So instead of going from the top to bottom, you go from the bottom to top. You assemble the layer by layer, right? You deposit the material and create them. So that is called a self-assembly surface, right? So and these surfaces also have some own debris, right? So it's this tools and this technology is is making us to think in that think about this nano tribology. So when we talk about the tribology, it is about the surface defect, it is about studying the surfaces, right? So at micro scale, we have to study this micro or nano tribology. So how are we going to measure that surface defect, right? So suppose you have this scanning probe microscopy, or you can say AFM, right? And tunneling electron microscopy. and many other microscope tools are there to measure the surface or to characterize the surface. But some of them, most of them are make contact with the surface, right? Without contact, it is not possible to study that surface, right? So some of them require the conducting surface to have this image acquired. For example, SEM, you need to have this gold coating or some conducting material coating, then only you can read it properly. And similarly, some need some tapping mode, some continuous mode. Different mode of operations are there. For example, in AFM, you have this cantilever. So that cantilever will continuously tap up and down, and it will continuously measure the deflection, right? In that way it will measure. So the surface contact, so the measuring instrument is creating the surface contact with the surface, and that also it should be proper. For example, this red color one is our contact probe, and the green one is our surface, and this probe is touching our surface. But if you look into this micro scale dimension, the probe and this surface is not continuously touching, right? There are some gap in between them, right? Because of the surface roughness, this gap is there. And also the probe needle, right? The needle of this probe, that is also very flat. Some kind of irregularity is there in the flat needle, right? We consider them as a flat, right? But when we look into that micro level, we see that that needle itself is not flat, it is having some kind of roughness. So how are you going to handle this, right? That is the challenge. So we need to have some kind of model, right? The solution is that we need to have some model. So it is not possible to have this perfect needle, right? Without any roughness, it is not possible. So even though you take any metal or material, whatever it is, so there would obviously there will be some roughness. So only thing is that we have to handle that roughness by creating some model or creating some approximation out of that model, and subtract that defect what we have, right? So that is the solution. Then we also have because of this kind of no, that gap between them, that interfacial force is also not proper. So there will be imbalance in the interfacial force, right? So obviously there will be some adhesion force and cohesion force of these molecules. So this adhesion and cohesion force of these molecules, they are not proper, right? And this imbalanced force will trigger some additional energy, or it may reduce that energy, right? So that has to be modeled properly. Then some of the devices, like we have this COM drive, right? And we have this actuator, micro actuators, right? So they are designed to move. They have this proof mass. For example, this oscillators or the resonators are there, they have to be vibrated continuously, right? Continuously, it is programmed, or it is required to be vibrated continuously. So when there is a continuous vibration, obviously there will be a wear, right? That model, that particular that proof mass will continuously create some wear over the model, and because of that wear also our surfaces will get damaged, and we need to have that model properly. So how much is my stress, right? How much is my area of my proof mass, and that proof mass, how much stress it will be generated, and I need to have thorough understanding of that calculation, right? And some of the environmental effect also there. For example, you use them in the no, humid environment, then there will be some water molecules, right? And when we have this high temperature environment, for example in the nuclear chamber or reactor, where we are expected to operate in the high temperature, right? So it should withstand, right? And because of the temperature, the surface also will get modified, that we need to understand. Yeah, this is what I'm talking about, right? So you see this roughness. So this roughness is not uniform throughout. Whatever the roughness we have, some places we have the larger roughness, some places we have roughness but not larger, some places relatively very less roughness we have, right? So this imbalance is there throughout our surface, and because of this imbalance our interfacial forces will damage, or it will vary drastically. Some places like the capillary forces will change, electrostatic forces will change, and van der Waals force, right? That is the force between these molecules, right? That will also will vary. And this improper surface irregularity, right? So because of this surface irregularity, you have this various adjacent property also. some places will stick properly or quickly, some area may not be stick. For example, you attack the surface with some glass, right? So because of this irregularity, right, so this portion of this asperities, it will stick properly, but whereas this portion may not stick because there is a gap between them, right? So adhesion will be damaged. And also this roughness, various roughness will create some friction. For example, some slope and valleys are created, right? um, some hills and valleys are created. So and from the, obviously there will be imbalance force, and that imbalance force will make the particle or the next level of surface to have some, to experience some friction, right? So from the hill to the valley, the 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 force will be acting. So that kind of force we need to handle it. So the surface irregularities are very serious irregularity, and we need to model it properly. In the macro scale it can be overlooked, right? So anyhow we are going to use the approximation, the voltage or the current we get is larger enough to give us some kind of understanding. But when we scale down further, so this surface effect cannot be ignored, right? It cannot be overlooked. So although it looks very it is secondary effect, right? So it is not our intention to create this kind of surfaces, but then it is having, it is defaultly it is having some effect on our measurement, our design, right? Everything will be affected because of this surface irregularity. So we need to pay some attention, serious attention to this surface irregularity, then only our design will be correct. So this is what I told, this because of this wear, right? Continuously moving or continuous actuation, and you have, there is a dislocation of this joint, right? And there are some wear particles are damaged, dislocated, right? So there is amorphized oxide layer that is coming out without any polysilicon, that the polysilicon which was coated over this oxide, it is removed, whereas this portion you have this some polysilicon. So this kind of wear will take place for the continuous activation. And similarly, as I told, this adhesion also not proper because of this low contact pressure and augmented asperities. So if you want to stick to material, and because of this irregular surfaces, it will not stick properly. And also abrasive work, you see here, if it is high contact, you apply high contact, and because of this abrasive force there will be some crack, right? Some crack will be generated continuously if you apply the force, right? We need to calculate this residual stress. Many times we ignore that residual stress, right? But if you consider that residual stress, even though you place that force over the top, so after some time, so there will be a possibility of creating the crack. So that crack also would be generated. So we need to look into that. And the humidity is another source of the surface morphology debris, right? So it will damage. Yeah, here we see that that is a conventional CVD, that is chemical vapor deposition of this diamond film, right? Which is grown from this H2, that is 92% purity, and we have this methane gas, right? So it has been grown, right? CVD diamond film has been grown. So without properly, without any compensation, our surface is very rough, right? We see here very rough. But after compensation, that is, you add some argon, right? And you change the methodology. Instead of using that methane, you use that argon. So you change the methodology, and you see that relatively the roughness has been reduced. So surface finish is better, right? So we need to look into our methodology, right? Which tool we need to use, which chemical we need to use. We need to properly tune it. And even though you tune it, you reduce this roughness in a much better way, but still there are some roughness. So for this roughness we need to have this model, right? And we need to have this model. But the first step is that you reduce that roughness as possible, as possible. So you have to reduce that roughness continuously, so that at the minimum level we can apply the model to compensation. And similarly, you see here, when you look into the micro needle, right? The surface, it looks like the needle is very sharp, right? There is nothing inside on the tip of that one. But when you further scale it down and look into the tip, you see there is a hollow opening there, and that wall, right, it has to be properly having proper roughness. But here you see that this edge of this wall is damaged, right? And if this edge of this wall is damaged, then the drop, whatever is going to no come out of this needle, it will move more toward that outlet, means the opening. Before it going to the proper shape, it will be leaking from this edge. That is the thing. Another thing is that we need to see the stress, internal stress calculation, right? This cantilevers are freestanding cantilever, right? It can withstand without any no buckling, or it can stand nicely. But if you have to maintain that stress properly, so our stress calculation is needed. Yeah, next is about the self assembled monolayers, right? Instead of going from the top to bottom, we go from the bottom to top. Layer by layer, you deposit first oxygen, then silicon atom, then OH, right? In that way, you deposit them, then you build the structure, right? And in this way, if you do this, then the chances of getting the rough surface is less, right? You grow it from the atom, right? From the atom, then molecule level, then you build up from the bottom. So when you go from the bottom to top, the chances of developing the roughness is less. Whereas if you move from the top to bottom, obviously you use different tools like lithography or milling, right? All many things are there. So because of the tool, there will be some damage to the surface, right? But if you go from the bottom to top, the surface is comparatively smoother. But here also there will be some roughness, but you can handle it in a better way, right? So there are many applications, like if you want to deposit on the silicon, you need to use the silane SAM. Then gold, on the gold you need to use the thiol. And these are some of these applications. There are various way to measure that adhesion, right? So whether the particular two layers are properly stick together or not, right? How do you measure whether both are sticked properly or not? So you fabricate n number of cantilever with different size, right? And with different size, you fabricate n number of cantilever, and you try to examine whether whether the adhesion is this much level, or whether the adhesion is this much level. So various levels of if the adhesion is only this much, then obviously it is very poor, right? It is not stick properly. If the adhesion is means that stickness is up to this more, then you will have this good stickness, right? Good adhesion is better. So in that way, we check the adhesion based on this cantilever check. And how to avoid the roughness which is created due to the mass, proof mass, right? Continuously vibrating structure is there, or a moving structure is there, right? This is the one of the leg of this com drive, right? So this has to be moved in the y direction, up and down like this, right? When this is the default structure, right? You have this proof mass, and you have this end stopper to intact. So through this end stoppers, there will be some mechanical force that will be transferred to this metal electrode. So instead of that, you create some loose oxide flake. You deposit the oxide here and there, right? So if the mass is damaged continuously over the metal electrode, and then the metal will be eroded, right? It will be removed, I mean damaged after some n number of cycles, right? It will be damaged. But if you place this oxide in between, you put the oxide in between, then there will be some kind of cushion effect is provided. So because of that, the movement is obviously good, and there will be some kind of no the damage will be reduced, right? So this is what we see here. So instead of doing this oxide, you can also use some kind of polymer. So FDTS is one polymer which is useful for covering up. And here you see that when you do this without oxide, you see this damage, this much damage has been created. But after you deposit that oxide flake, the damage has been reduced. And similarly, without using this FDTS, you have this wear on the surface. but after using that, after coating that FDTS, you have this smoother, better, smoother surface over that. Yeah, and also how are you using the cantilever for measuring the surface, right? So for example, AFM, are we going to use this tapping mode or the free mode, right? So we have to determine, right, when we need to use that tapping mode and all. So by controlling that, we have to use, we can avoid some kind of roughness. There are some techniques also there. On the tip, you dip uh, some um, some no, dielectric polymer, right? On the tip, you dip some dielectric polymer or water film, they say. So then when you place that surface, actual surface, that effect is reduced. That damaging effect is reduced. So some kind of precautions, by considering some kind of precaution in the measurement, we can avoid this surface irregularity. Okay. Surface roughness, how are we going to measure that surface roughness, right? So this is the data available. Means with the X-ray lithography, we have the surface roughness of this range, right? And with the X-ray lithography with the micro milled mask, you have this 0.15 micrometer. Direct micro milling, you have zero point 0.1 micrometer or less. Micro drilling, you have best drilling is possible in this range, right? So in this way, there is some characteristic. If you consider any surface, any solid surface, you can classify them like this. That is homogeneous surface. Homogeneous means all the surface is having the same material. There is no different materials. All the material is same. Then it is homogeneous surface. And heterogeneous means there are various materials are there. For example, alloys. When one you have some one conducting layer is there, another is dielectric layer is there, then you have some contact pad is there. So that kind of structure is the heterogeneous structure. And the homogeneous structure means you continuously evaluate the one material. For example, silicon of same resistivity or the same more or less same crystal orientation, right? So that is homogeneous material. And then we have that homogeneous material can have these two kind of roughness: deterministic roughness or the random roughness. So deterministic roughness means you are able to see the irregularities regularly. So with a different space, for example, for every 1 micrometer you see the same irregularity. So that is the deterministic. And random means you don't know where the irregularity is there, but irregularity is present there, right? For example, you get the etching. Because of the etching, you have the some irregularity, right? So you may not get the uniformity, right? So that is not that is indeterministic, where you will have the more chemical will be taken out. uh, so more the surfaces would be etched. Some places the surfaces may not be etched as it was, right? So that is the random surfaces. So the random surfaces can be isotropic or anisotropic in nature, depending on the directional orientation. And isotropic surface roughness can be classified mathematically into Gaussian surface or non-Gaussian surface. Gaussian surface means you have this kind of bell kind of pillars over the surface. Non-Gaussian means irregularity. It is not following under that Gaussian distribution. So the surface is very random, right? So that is the non-Gaussian distribution. So usually these are the parameters we use to take from that surface roughness. So I will talk about the surface roughness and surface wetting. There are many irregularities are there right now. So I just want to focus on the surface roughness and surface irregularity, surface wetting. So the surface roughness can be measured in this particular range, like average roughness, right, or RMS roughness, maximum peak height, maximum valley, right? So that is maximum topmost surface is the maximum peak height, and the minimum surface height what we can measure is the minimum valley. So and maximum height difference also can be taken as a one measurement. Skewness, right, how much it is skewed and how much kurtosis, right, average difference between the highest peak and the lowest valley, right? And power spectral density is another popular measurement tool which will give you the characteristic in the spatial distribution, right? So among all these things, except this power spectral density, all these things would give you the amplitude or the magnitude characteristic only. For example, average reference means how much height, how much height, that is only, right? Average height and how much RMS height. So they all would give you only the amplitude weight height. Whereas in the power spectral density, you will have this uh, spatial distribution also. But this is very critical and very computing this PSD is time consuming, and it is difficult to handle. But it will only provide the spatial information, whereas others only will give you the amplitude information. So as a new approach, so we also can use this fractal surface characterization. So the instrument means how obviously we know that which instrument we are using and what resolution we are using, that will determine our characteristic. For example, I say the average roughness of some 3 nanometer, right? But how many data I have taken, how many scales where I have measured, right, and how many images I have taken. So all these things are if you increase that number of samples, right, obviously that average will also go up or go down, right? So depending on that instrument and the methodology, parameter will change. So the average roughness, I say that 3 micrometer may not be same, right? So it will vary, depends on how many readings I have taken and how many images I have captured and how I analyzed it, right? So that is not a very good information. So what we need is that some kind of measurement unit which will give you the amplitude information as well as the spatial information. So the fractal dimension will help you to achieve that. That is fractal based approach can give you the amplitude as well as spatial information. So fractal is nothing but the expanding symmetry or the evolving symmetry. So mathematically they can be identified as the complex object. Means the minimum object which is repeating itself, that is called a fractal. So for example, if the repetition is exactly the same at every scale, it is called a self similar pattern. If the fractal is different, right, but it is repeated every time, right, then it is called a self affine pattern. So we have to notice whether it is self similar pattern or self affine pattern. So based on this feature, you have to extract that fractal dimension, right? So this dimension study is not new to us. We know that if you draw one line, that is one dimension line. If you draw a square, then it is a 2 dimension, and if you draw the cube, it is a 3 dimension, right? But why are we restricting with the odd numbers? We say 1 2 3. Why don't we say 1.5, or why don't we say 2.2, something like that, right? But we are not saying it doesn't mean it doesn't exist, right? So there is a dimension between 1 and 2, and similarly there is a dimension between 2 and 3 also. So that dimension is called as fractal dimension, and that fractal dimension is based on this self similar pattern or the self affine pattern. So this is what I am talking about. There is a line is there, right? We call it as a one dimension line, right? But if you twist it like this, that is, you break that line into 3 different portions, right? And there are 4 different portions with 3 different scale, right? So 1 2 3 4 different portion and 3 different scale. So 1 by 3 1 by 3 1 by 3. So this is the first portion, and then you break this further in the same way. This is called as self similar pattern, because we are following the same way of breaking them into further, right? Because of this, it is called a self similar pattern. And obviously if you further scale it, again the same pattern is scaled here, again the same pattern is scaled in this direction, in this direction. So we are scaling it in a self similar pattern. So you continuously you do this scaling, and you what we can observe is that this particular structure, you do this mathematical calculation. So log n by log m, it will give you the dimension of 1.26. So this is called as fractal dimension. So this fractal dimension is the dimension which will tell it is more than one. Obviously it is more than one, right? It is not a line. So this particular, we started with the 1, but we ended with not 2, right? 2 means completely filled, right? But it is not completely filled. So it is in between 1 and 2. So by measuring this number of division and number of scale, we can say that this fractal dimension is 1.26. So it is in between 1 and 2. So 2 means completely filled, and 1 means just one line. So in between 1 and 2, we have this fractal dimension of 1.26. So we already have much study about this fractal dimension, fractal geometry, right? So this is very useful when we model it, right? When we go into the deeper and deeper, we can have the self similarity or self affinity features are there, because we are going to use the same chemical for etching, right? Are we going to use the same no lithography, no light rays for the fabrication? So there must be a self similar or self affine pattern. So if you find out that self similar and self affine pattern, you can directly calculate the fractal dimension. That fractal dimension will help you to have the roughness information in the amplitude as well as in the spatial scale. So how do we get this? This is the equation. We have this Mandelbrot Weierstrass Mandelbrot function. So according to this Weierstrass Mandelbrot function, this is the equation, right? So this epsilon minus infinity to infinity, that is the space what we are going to compute, and we have this d term here. So this d term is nothing but the fractal dimension, and we have this k, and this multiplier, and this is for the phase angle. So if you substitute this fractal dimension, you will get the information for amplitude as well as spatial information in the form of rough profile, right? So this is the fractal dimension. So here we see that I have simulated this fractal dimension with various surfaces. So 1.1, 1.2, right, 1.4, and it is 1.9. After that, it will be 2, which is completely filled square, right? So this is the fractal dimension with various scale. So you see there is a relationship between the RMS value of this roughness and this fractal dimension of this roughness. So there can be a relationship. So from fractal dimension, you can also compute the RMS value, or if you have this RMS value, also you can compute the fractal dimension. So there is a modeling this technique is there. So with this modeling, what we can do is we can estimate the parasitic capacitance, right? So you consider the two parallel plates, right? What we say is there is a two parallel plates are separated by the distance, and the distance between them is calculated, and we estimate the capacitance. Okay, epsilon A by D, but the D is not as we expected, right? So the D may vary due to the roughness in the surface. So the D in the roughness in the surface is varying, means the capacitance also will change, right? In that way, by studying that fractal dimension of the surface or the roughness of the surface, we can estimate the parasitic capacitance. So this is the exact model, right? So you determine the fractal dimension from the experiment, you model the surface based on that experiment, and you calculate the electrical parameters like capacitance or inductance or resistance or electric field, right? All these things you can compute, and you can develop your compact model. So you can estimate that this much capacitance I can ignore, or I have to be serious about my design, right? So that information can be extracted from the surface roughness study. We have done this. So like one surface is considered as a rough surface, and we see that how the rough surface is varied with respect to the different fractal dimension, and how this electric field is varied with respect to fractal dimension, and this is resistivity changes with respect to fractal dimension. So this is about the roughness, and then we have this surface wetting, right? So this is again the surface wetting can be a hydrophobic or hydrophilic based on the uh, contact angle it makes on the surface, right? So suppose you place one water droplet on the surface. If the droplet is completely wet, then it is hydrophilic. If it is not wetting, like we saw in the example of the lotus leaf, it is not wetting, then it is called as hydrophobic, right? So there is a contact angle equation provided by the Young's Thomas Young, the popular scientist. So this is called as Young equation. This will give you the contact angle. So how much contact angle is there from the surface? So with the help of the surface wetting, we can also see the dynamic of this contact angle, whether it is how much angle it makes to the surface. So the surface can be tuned so that this contact angle can be generated. Means you want hydrophobic surface, so you have to tune it such a way that you create some roughness over the surface. So because of that roughness, this contact angle will be larger than the 90-degree, then it is hydrophobic, right? And similarly, you want the hydrophilic surface, you create some surface roughness, right, with the help of some light radiation or some mechanical polishing, right? And the it will make the wet it will make the surface to wet completely. So in that way, we can create the hydrophobic or hydrophilic surface based on the surface roughness. So in fact, there are many mathematical models are there. These are the popular mathematical model for this study, that is Wengel model and Casey-Baxter model. So we have this pillar structure considered, right? Uh, in in uh, in actually in practice, we won't have this regular pillar structure, but for the study purpose, this regular pillar structure can be studied and it can give us the valuable information. For example, this is the Wengel equation. Wengel equation is for the hydrophilic design where the drop will wet completely. Whereas the Casey-Baxter equation is the hydrophobic structure where the droplet will not touch even the surface, but it will hold on and it will roll. So this kind of structure is useful if you have the very less sample, right? And you want higher velocity of the droplet, then hydrophobic is preferred. But if you want more adhesion, right, more sticking to the surface, for example, painting, right? For example, you want to have the some kind of painting on the surface, then this Wengel state is preferred. But you want non-wetting surface, right? So then we have the Casey-Baxter state is preferred. So based on the height and this width of this pillar, that is A is the height and B is the width of this pillar and H is the height. Sorry, surface area A is the surface area from the top, and B is the width of this pillar and H is the height of this pillar. So based on that, we have this equation and F is there, and by varying this F, in fact, you can move from hydrophobic to hydrophilic. So that is the information we get from this, right? There is a critical contact angle. So by tuning this A, B, and H, we can move from the Casey-Baxter state to the Wengel state, and similarly Wengel state to the Casey-Baxter state. So if you can control the roughness, you can control the wetting. So that is the conclusion. Yeah, quickly I will just go through the case studies what I have done previously. So so what I developed with the micro mixer from the PDMS. So PDMS is the transparent polymer. So this is the PCB mold. Instead of UV lithography technique, I use this PCB mold technique where the pattern will be generated on the PCB itself. Then I pour the PDMS over the PCB mold and I apply the temperature treatment. Then this when I pour it, as it is a PDMS is a liquid, but when I heat the PDMS, then it will become solid like this. But it is having some elasticity because I mix it in the proper ratio. So I have this elastic PDMS micro channel. It is Y channel. Then I place the PDMS on the spin coater and I bond this PDMS with the glass, because this Y channel has to be closed. So then only the fluid will pass through the inside this channel. If the channel is open, then it will come out, right? The fluid will come out. So the fluid has to be closed with the glass. So that is bonded with the help of this spin coating. Then this is the final device. So what from this study, what I can say that I am coating the PDMS over the glass. Then I attach this surface over the glass and I do the temperature treatment. So because of this coating, based on this coating, there will be some surface roughness, right? So that surface roughness has to be studied, and that surface roughness, how it is affecting my flow characteristic. So that is my study. So what I have done is I measure the fractal dimension. So I taken the AFM image with various scan size, right? 60 micrometer by 60 micrometer to 600 nanometer to 600 nanometer. So if you look into the RMS value, here you will get the different RMS value, and here you will get the different RMS value, right? By simply telling the RMS value is not useful, right? It depends on the how much scale we are varying, we are seeing. So here we will get the different RMS, here we will get different RMS. So RMS value is not useful. So fractal dimension is useful. So I plot the fractal dimension. So what I have is, instead of having the self affinity, what I seen is I put the different perimeter of the hole. So I calculated the number of holes here, and I fitted it with the perimeter of that hole, and I plotted the data perimeter with this scanned area. Then I get this fractal dimension 1.4. In fact, this fractal dimension estimation is done with this software tool. So we no need to do much calculation. Only thing, we need to upload that images, right? So you upload the various AFM images, and you say the methodology. There are various methodologies they have. One methodology is that, perimeter of the fitting hole. That is one methodology. Another methodology, different methodologies are there, and this is having better accuracy. So I have taken this methodology, and I found out this fractal dimension to be 1.4. So this is my roughness I get on the PDMS surface, right? So I also do this characterization experimentally. So I place this microscope, and I put the fluid in the syringe pump, right? And the fluid will pass through the micro channel, and the velocity is measured with the help of image processing. Velocity is measured, and mixing efficiency also measured with the help of image processing. So you see that here in this image, we see on the bottom surface there is some surface roughness. I also simulated, right? So previously what I shown is the experimental characteristic of my fluid flow in the microchannel, and I have done this with the CAD simulation. So simulation results also I seen, and experiment also I seen. With the simulation, what I can see that if the roughness is more, obviously your velocity is less, because the more roughness, the fluid rate would be reduced, because it has to go to the top, as well as it has to go through the to the valley, right? And the flow would be disturbed. So it is not smooth flow, right? So obviously here you see there is it is not smooth flow. So because of this improper smooth flow, so there will be a roughness, and roughness will affect my velocity. So this is my velocity characteristic, and this is the experimental characteristic with roughness model. Without roughness model, I see that with roughness model, it is somewhat similar to the experimental characteristic. But if you don't consider the roughness, you see that is what I am expecting is a flat result, but it is not correct, right? So experimentally it is showing something different. So I need to consider the roughness in my simulation. So with the roughness in my simulation only, I can see the exact replica of my experimental result. And you see the difference in the roughness. It is 10 power minus 4, right? So the concentration of the mixing efficiency is very less. The mixing efficiency also improved due to the roughness, right? So because there is some kind of turbulence is created inside due to the valley and the height of this peak of this surface roughness, some kind of turbulence is created, and that turbulence is very less, but it is having some improvement. That is what I reported here. 10 power minus 4 is very less scale, but when you look into the nanoscale, this may become significant. Yeah, so next study is about surface wetting. So this is one example. Yeah, so this is the new technology, that is electrowetting on dielectric based lab on chip, where they apply the electric field. With the application of this electric field, this droplet will move and it will merge, right? So by applying this electric field, we are changing that contact angle. So when there is a change in the contact angle, the droplet will move from one place to another place. That is the principle behind that. But what we have done is, means it is having some advantage, like it is having some high throughput and less sample consumption, and it can be reprogrammed, reconfigurable. You can move the droplet at any path. That is advantage. But disadvantage is that whatever the fluid we are using, that is conductive, because you are applying the electric field on the top as well as on the bottom. So the fluid has to be conducting in nature. So that is a disadvantage. And dielectric layer, what we have, what we provide in between the metal and the liquid droplet, it has to withstand the high voltage. At least there should be 10 volt, minimum of 10 volt has to be applied for moving the droplet. But it is also not good, right? Because some dielectric, with this thin dielectric layer, it may damage the pad. That is the disadvantage. Another is application of the high voltage for the biomedical use, right? So they are using the lab on chip for the biomedical application. Suppose the blood separation and other things where people are using. So we are not we have to study much about this, right? Whether it will damage the soft tissue or not, whether it will attract that biological compounds in that fluid or not. So all these things are unknown to us. So as an endeavor to that, right, what we have done is we have generated the surface roughness. Based on the surface roughness, we are tuning the surface so that it will move from one place to another place. For example, you design a pillar in this surface, in this model, like you provide the less contact area here, and you provide the more surface area here, and here this is hydrophobic and this will become the hydrophilic. So when you place the droplet over this place, the droplet will have some surface force, right? And the surface force will pull the droplet toward the more hydrophobic area. So this is visible here at 0.1 millisecond. The droplet is here somewhere, and at 1.6 millisecond, the droplet moved toward the right side. And this also can be seen from this video, right? So by developing the surface technology alone, we can move the droplet. There is no need to apply the external voltage, right? If you don't apply the external voltage, means you can avoid the secondary effect. You can very well utilize for the biomedical application. And this study also have been reported, means how these edges are moved, how the positions have changed, how the contact angle are changes dynamically with respect to time is also provided. And instead of one droplet, we can also move the two droplet by designing properly, right? Both the edges are hydrophilic and central is hydrophobic. So you see that the droplet is moved and attracted towards each other because of this surface force. So instead of using the electric force, so we are using the surface force. So it is difficult to use the 10 volt supply at the micro or nano scale, right? So instead of that, we can use the surface force. And this is another example. By designing the proper surface, we can also split it. Splitting of the droplet required more power or more energy, right, than the merging operation. So transportation is easy and merging is easy, but splitting is required more energy. So that more energy is provided by designing this kind of variation in the height of this pillar. So if you design like this, then we will have this more uh, energy required for splitting of the droplet. But designing this or fabricating this kind of structure is very complex. It requires much higher lithography steps and all. So but over the improvement of the technology, it can be achieved. So finally, I would like to conclude now. So what we see from the MEMS evaluation of the VLSI technology, MEMS technology also existed, right? And various methodologies, fabrication techniques are being used, right? But we cannot underestimate the surface effect, right? So surface forces or surface energy is very dominant in the micro or nano scale, so which was overlooked in the past. But we no more we can overlook it, and we need to consider it. And in fact, we can use the surface energy for our own advantage. So some of these two cases what we discussed, we have utilized the surface energy to our own advantage. So one for the surface roughness to improve the mixing of this micro mixer, right? And also to improve the velocity or to study the velocity of the micro mixer. And also you can use that surface roughness to design the lab on chip for merging the droplet or splitting the droplet without applying the external force. So these are the some of the things I want to say. And instead of using the generalized surface roughness parameter, we can use the fractal based surface roughness parameter, which will also give you the amplitude as well as spatial information, which is very much useful for our study. Thank you very much.
Thank you, sir, for your wonderful lecture on handling surface issues in MEMS. You have given very nice explanation about surface and bulk micromachining techniques. Thank you so much for your lectures on handling surface issues in MEMS. We hope our participants have gained a lot of information from your talk. Participants can ask your queries. Now the session is open. Participants can ask your questions.
Sir?
Yeah. Yeah, I can hear. Yes,
Yes, sir. Sir, if we are fabricating lab on chips, there will be a lot of complications in the structure, right, sir?
Yes. Yeah. There will be a reservoir. There will be a micro channels, and some pillars would be there. It is complicated.
So there will be stiction problem too, right?
Yes.
Is there any way to avoid stiction in that?
Yeah, it is. Right now, people are using that PDMS, right? Polydimethyl siloxane. That
Yes,
polymer
sir.
is used because it is giving you the advantage of flexibility and optical visibility, right? And it is lower cost. But it is having some disadvantage of the stiction, as you mentioned.
Yes, sir.
It is having the large pinning effect. So to avoid the stiction, actually I skipped this step. Maybe I will go back. There is a pinning effect. So yeah.
Okay.
So here in this contact angle, so we see the three phase contact line, right? So the sticking is taking place over the surface. So the movement, the free movement of the droplet not just depends on the surface area, but it is largely depends on the contact area. So means the edge of this two contact line. So if you can somewhat manage this contact line hydrophobic, right, some kind of cushion effect you provide on the edges of this contact line, then it is
Okay.
easy to droplet to roll off. So what people are suggesting is that instead of putting the rough surface over the surface, you place the rough surface only at the contact line, right? That contact line would help you to easily roll off. So this is the one way of avoiding the sticking in the surface, but it has to be engineered properly. Means you cannot reconfigure once you design that this area I will have this surface roughness, then you have to place the droplet only at that area. That is the disadvantage. This is
Okay.
one thing that we can avoid sticking. Another thing is that people are using some spray like never wet spray and other sprays are there. So they are hydrophobic spray. So it is having some roughness. So it will create some roughness over the surface. But we don't know how it is reactive, whether it is highly reactive to the biomedical compounds or not. It is not fully known to us, but it can also avoid sticking.
Okay, sir. Okay, thank you.
Participants can raise your question. Hello, Praveen. Hello, Dr.
Yes,
Praveen.
ma'am. Yes, ma'am.
Thank you so much, Praveen. Your talk on this particular topic is very informative. The participants also, they have gained a lot of information from your speech. So you explained that in a nice manner.
So thank you so much, Dr. Praveen. I think no no questions from participants. So from this, what we can very it's a wonderful. They understood well. That's
I
what.
hope so. It's my pleasure, ma'am. So very pleasure to interact with you all. Thank you for giving me this opportunity.
Yes, yes. Thank you, Praveen. Thank you so much.
Thank you, ma'am.
Okay, okay. Dear participants, what about the yesterday? You got the attendance or not?
No, ma'am. Today only have the attendance, ma'am. Yesterday, we are not filled the attendance form, ma'am. Only filled feedback form, ma'am.
Okay, because in the yesterday I asked to send that attendance form in all of your registered mail ID, but I don't know, I didn't confirm. But anyway, in the afternoon I will post it.
Okay, ma'am. Okay, ma'am.
Okay, okay. In the shortly in the afternoon session, one of the professor Nitin Kale, so he is going to handle that section. So please be in time. Thank you. Hello, sir. Sir, good afternoon, sir. Hello. Hello, sir. Is it audible, sir? Can you hear me? Sir? Sir? Yeah, adding a Sir, hello. Sir, welcome you, sir. Sir, can you hear me?
Yeah, I can hear you. I can hear you.
Yes. Good afternoon, sir. I welcome you, sir, on behalf of Department of Electronics and Information Engineering and participants. Shall we start the session, sir?
Yes, we can start.
Just wait for a few minutes, sir.
Yeah.
Just
What I will also do is I'll just try to upload my presentation.
okay. Yes, sir.
Good afternoon, everyone. Welcome back to the first lunch session of G2.
There is an echo at your end, so somebody's mic is giving a problem.
Welcome back. This session will be engaged by Dr. Nitin S. Kelly, who will deliver a talk on microsensors and instrumentation for sensing. Before handing over the session, this is a brief info about him. He completed his MTech from VNIT Nagpur and obtained his PhD from IIT Bombay. He was the co-founder of NanoSniff Technology, a startup company incubated at IIT Bombay, where he is responsible for R&D in research and MEMS, microsensors and instrumentation. He has demonstrated a device for detecting explosives using microheaters and a proof of concept for detecting cardiac proteins using piezoresistive cantilevers. His research interest mainly deals with designs, fabrication, characterization, simulation of MEMS devices for chemical and biochemical sensing. He has published more than 20 journals and two book chapters. He holds 4 patents with him. We welcome you, sir. Now I request you to deliver your speech on microsensors.
Okay, sure. Thank you. So first thing is I'm just trying to share my presentation. Please tell me if it is visible in full screen. Yeah, is it visible?
Yeah, it is visible, sir.
Now in full screen?
Yeah.
Okay, just I'm trying to change a couple of slides.
Sir, please, sir, could you check? It's not a full screen actually.
It is not?
Yeah, yes, sir.
It is not full screen, is it?
Yes, sir. Okay, sir.
It's okay, right?
It's in full screen only. You can continue, sir. No.
Okay.
Okay, sir.
Okay, so thank you, Professor Kavitha, and your faculty colleagues and your institute for giving me this opportunity to present our work to your FT. So essentially, today we are going to discuss about some of the microsensors and nanosensors and instrumentation, which NanoSniff Technologies, that is our company, has developed for detecting chemicals and biochemicals.
Sir, excuse me, sir.
Yes.
Sorry for disturbing you. Actually, your voice is breaking, sir. Actually.
Okay.
Check your mic.
So I am close to the mic now.
Okay, okay, sir. Okay, sir. Okay, sir.
Yeah. So as I was saying,
Okay,
today
sir.
we will discuss about some microsensors and instrumentation that has been made by NanoSniff for chemical and biochemical sensing. So NanoSniff is a company was incubated at IIT Bombay. We work in the area of microsensors, that is MEMS sensors. So I'll be talking about them. But even before that, a little bit about other MEMS sensors. There are some devices like micro hot plates and micro cantilevers. We'll be talking about them. We have a product called Nano Sniffer. It's an explosive trace.
Sir, excuse me.
Yes.
Please switch on your camera, sir, so that
Yeah.
we.
Hold.
And thank you very much, sir. You can proceed.
Yeah. Okay. So do you want me to keep the camera on?
No need, sir.
Okay.
Just want to take your
Because
screen
yeah,
cap.
because the bandwidth is sometimes a problem.
Okay, sir.
I'll switch off the camera.
Okay, sir. Okay, sir. No issue, sir. Then you can switch it off.
Okay. So as I was saying, we are a company incubated at IIT Bombay. We have engineers doing sensor design and nanofabrication. We work on certain chemical coatings, surface chemistry, a good amount of embedded systems in terms of hardware, software, co-design, etc. And we do a little bit of biochemical processing. So that is what I'll be talking about. So we know, when we talk of how small is small, in terms of size, we need to have some sort of a perspective. What you will see here is a macro object. So these could be bridges, these could be aeroplanes. And then you have some structures which are called as the mesoscale structure. These are the structures that we hold in our hands and we can play around. After that, still smaller than that, that is, you have the micro scale structure like bacteria or the cells or the hair. And then, so these structures are typically those structures which are visible under a microscope. So it's very hard to see human cell or a bacteria without the aid of a microscope. And finally, since we are now all aware of viruses very well, you have the nanoscale structure, are the viruses. But besides the viruses, you also have the nuclei, cell apparatus, what is there inside the cell, many of the proteins. And since many of us are from electrical and electronics background, the transistors are also the MOSFETs that we are using in our chips, in our mobiles, in our laptops. They are also a good example of nanoscale devices. So in this slide, you will see a couple of pictures. Look at this particular picture. And I'm trying to show what happens to certain properties, what happens to certain materials at the nanoscale. We know that there are two important force laws. One is the Coulomb's law, which governs with the charges, and second is the Newton's gravitation law, which governs with the masses, the weights. So if you look at this picture, you will see two balls. They're having, let's say, mass of m1 and m2. And because of gravitational force, they will be attracted by force which is equal to m1 into m2, which is proportional to m1 into m2 upon r square. Similarly, if these were charged, then they would be attracted or repelled, depending on what is the polarity of the charge, which could be q1 into q2 upon r square, proportional to that, assuming that q1 and q2 are the charges. Now, here is something interesting. Suppose if you reduce the size of the object, then the gravitational force is going to reduce. But they can still hold the same amount of charge. And therefore, the force of electrostatics is not going to change. What I wish to show, or what I wish to say, is that for small objects, or objects which are having small sizes, it is the electrostatic force that is, and not the gravitational force. So this is one important concept. Second, we are all aware of certain nano effects. For example, in our MOSFETs that we are using today, everybody, I presume, knows what is a MOSFET. It is a metal oxide field emitter transistor. Sorry, field effect transistor. So in that MOSFET, the thickness of the gate dielectric today is less than a nanometer, or it's about a nanometer. And a couple of years back, when silicon dioxide was used as the gate dielectric, the problem people started facing was the effect of tunneling. And this was because the current was flowing through the dielectric. So people had to devise a material called as the hafnium oxide, which had high dielectric constant, and their problem was. But important thing is that at small sizes, the quantum mechanical behavior, nanoscale effect. The third thing that you can see is this cartoon, which is at the bottom of the slide. So you will see here about 5 vials, which are having liquids that are of different colors. And below them, you are seeing some nice spheres. So these are actually gold nanoparticles. And through this, what we are trying to depict is that the colors of the solution are a function of the size of the nanoparticles which are present in the solution. By this, we should understand that by tuning the size or by changing the size of the nanoparticle, you can change the optical because the color has been changed. The other thing that happens at nanoscale or the micro scale is depicted in this particular cartoon. What you see here is that, let us say, so what I'm trying to talk is about the importance of surface to volume ratio. So here what you see is a cube which is having a side of 1 meter. So the volume is 1 meter cube and the area is 6 meters. Suppose you divide it into halves. So there will be 8 parts. Now the the volume is still going to be the same. Please keep that in mind. But the area is going to increase. You go on dividing it, the volume will still remain the same. Area will go on increasing. This is because the areas that were inside this block, they have now become exposed because you have sliced that block. So now those areas are going to show their effect. And if there is let us say a chemical reaction, then it is that area that is going to be. What we wish to say is that at small sizes, the surface effects become very dominant, and what is inside that material, what is the bulk property, becomes less dominant. This is another important consequence. A couple of things that you can note is that nanotechnology as such is not really new, because let's say people, Romans for example, they could color glasses. They actually mix certain particles in a molten state of glass, and they could have colors, let's say red color, green color. Similarly, hair dyes have been used for thousands of years, and which were again some sort of solvent with black. And the third example is from India, from Ayurveda, where many of these bhasma preparations were known to contain nanoparticles. Okay. There are certain laws which I won't say these are not laws, but these are essentially phenomena that happen if you reduce the size of any particle. For example, the volume, it's going to reduce by L cube if it is scaled by a factor of L. The mass also gets scaled by L, and there is a list of all other things that can happen. I will draw your attention to one aspect, which is the frequency. So we know that every structure, everything, this building, this laptop, this earth itself, and many of all the structures, even bridges, they have a frequency of vibration. It's their natural frequency. What I'm trying to say here is that if the length reduces, the frequency is going to increase. Then you can also see stuff like, let's say, heat capacity, heat flow through small surfaces or through small objects. Heat is going to flow very fast. I'll give an example later on. The third thing is turbulence. Turbulence is something that does not happen at small scales. It's very difficult to mix liquids if they're flowing through microtubules. In terms of volumes, so typically, if you look at if you look at a volume which is, let us say, 1 liter. So now 1 liter is the milk pouch that comes at our homes, and the size of that pouch is about, let's say, 10 centimeters per liter. Now suppose if you scale it down by a factor of 10, so it becomes 1 centimeter by 1 centimeter by 1. Then the size now becomes 1 microliter. Sorry, 1 milliliter. It's not a liter anymore. It is 1 cc or 1 milliliter. You again scale it down by 10. Then it becomes 1 mm by 1 mm by 1 mm. That is a microliter. Further scaling down will give you nanoliters, and that's fine. Why this is important? Let us assume you have a situation where you are doing investigation of, you are doing some sort of a diagnostic of a person. And for doing the diagnostic test, let us say you require 10 milliliters of blood. Let's say 5 milliliters of blood, which is typically drawn from the human, from the syringe that they are using. Now, if you had a laboratory or if you had devices which could work with a tenth of the quantity, or which could work at 1/10 of the size of the volumes that you are using, then you could actually have been doing testing with a microliter or perhaps with a nanoliter. Now, this does not 4 to 5 microliters if you are giving a blood sample once in, let's say, 6 months when a person is unwell, that is not a problem. But if a person is, let's say, aged and is admitted, let's say, is in the ICU, then drawing 5 milliliters of blood is very difficult. Patient as well to actually be able to give that much amount of quantity. So for them, if you could make a device, if you could make a diagnostic test, and people are actually doing that with the help of chip now, then you could have done these experiments with, let's say, a milliliter or a microliter or a so that's right. And this is the reason why we want to make things very small, because it consumes less material, it consumes less power, and it consumes less resources. Okay, so this, what I have discussed was about why you want to make things small. Now, looking at the things themselves that are small. So these are the object of the talk today, microelectromechanical or MEMS. So in some places they are called as microsystems, some places as machines. And when they become really small, when the feature sizes becomes less, let's say less than a micron or so, then you also call them as NEMS or nano electromechanical systems. Now this is a slide which tries to depict the market of MEMS devices. Unfortunately, only up to 2016. But what this tries to tell you that today MEMS is a multi-billion-dollar market. If you just open up your cell phone, you will see a lots of MEMS devices. You will see, for example, a microphone. You will see a speaker. Both are MEMS devices. There is an accelerometer inside, which is a MEMS. There are a couple of oscillators, which are also again MEMS devices. There might be, so for example, you have compasses nowadays in the cell phones. So those are also MEMS devices. So some sort of micro electromechanical systems. And please keep in mind that today you would be reading in newspaper that there is a shortage of there is a shortage of sensors, because of which people are not able to make cars or motorcycles and stuff like that. And this is actually a big problem today, because during COVID, people had actually shut down their fabrication line. After COVID, now the market is up and people want to buy stuff. But then where do you get the sensors from? In a car, there are so many sensors. It has to measure your speed, it has to measure the fuel content, it has to measure the pressure of the tires, the flow of the fuel to the engine, etc. So MEMS devices are very important. And in the coming world that has become, that is Internet of Things, again what you have at the forefront are MEMS devices. Okay. So what does nanosniff do in MEMS? So we primarily make two types of devices. First is a micro cantilever. Second is a micro heater. So before getting to micro cantilever, little bit about heaters. Sorry, before talking about micro heaters, the slide in front of me is micro cantilever. That is the logical way in which we are going. So micro cantilever, as you can see, is again a structure which is having, let's say, a length of L, a width of W, and a thickness of T. And it is connected to the substrate at what is called as the hinge. What you can also observe is that the length and the width, these dimensions, are much, much greater than the thickness. This is something that is noticeable. This tells you that the surface area of the micro cantilever is much, much greater. You cannot compare volumes with surfaces, but you can see that you have a huge surface and the volume is small. So that is what. Now, what can happen with a micro cantilever? They said that every structure has its own natural frequency of vibration. You also sometimes call it the resonant frequency. So first thing that a micro cantilever can do is it can resonate. And if there is a small mass that gets absorbed onto the cantilever, then its resonant frequency is going to drastically. So it becomes a mass sensor. Now you cannot use this sensor as a weighing balance or in your weighing balance. Let us say to measure or your greengrocer, or your fruit seller. That person cannot use this. But if you want to make a very sensitive measurement, if you want to, let's say, weigh the presence or absence of a molecule, then you can. And people have actually measured, attogram level of sensitivities using microphone. The second application is a chemical reaction. What you see here are two cantilevers two materials actually connected back to back in a cantilever. And let us say you do some sort of a chemical reaction on the cantilever surface. Now we know that chemical reactions are either exothermic or so either there will be an increase in temperature or there will be a decrease in temperature. Now, these are two different materials. So they are having, let us say, they are having different coefficients of expansion. So if there is a temperature change, and because they are connected together, they will expand, obviously, but because the TCE is different and they're connected together, they will either bend upwards this way or they will bend down. So now bending is a signature of temperature change. Just as in the previous example, in the case of mass change, the change in the resonant frequency was an example of an adsorption of mass. Here, the change or there is a deflection, and that deflection now becomes a signature of the change in temperature. There is one more very important application, and that is called monitoring the change in surface stress. Let us take an example where you have antibodies. I presume that because of COVID, everybody knows what is an antibody. So let us say the antibodies to the coronavirus are coated on the surface of the cancer. And now you are passing, let's say, a blood sample or a swab sample, throat swab sample, which is having coronavirus in it. And since coronavirus particles are there, or those viruses are there in the swab, and since the antibodies to those viruses are present on your cancer, then what will happen? The principle is that antibody-antigen interaction is highly specific. Therefore, these viruses will go and interact, it will go and stick and attach themselves with the antibodies. Because of this attachment of the antibody and the antigen, there will be a change in the surface energy or the surface stress. Because of the change in surface stress, the cantilever is going to deflect. Therefore, deflection now becomes a signature of detection of coronavirus by the coronavirus antibodies that you had coated on the candidates. This is one very relevant example. I'll give you how we use it for some other purpose. The cantilevers, they undergo what are called as either tensile stresses or compressive stresses. And what I was trying to show in this slide is that you can see that this portion is curved, so it is a part of a circle. This portion is also curved, so this is also a part of the circle. So it has a certain radius. That radius can be found out if you know the Young's modulus, that is the material properties of the device, and some of the other quantities which are related with the geometry of the device. So if you know that, and if you are able to measure the radius of this curve, then you will be able to find the value of sigma, which is the surface stress, which I had just talked about. Similarly, if this cantilever was straight, it would have been something like this. But now it has deflected by this much amount. This deflection is called as Z or delta Z. That delta Z is also related with the material properties, let's say the Poisson ratio and the Young. And it is also related with the dimensions, let us say H and F. And if you know all these quantities, then you can find out sigma, which is the surface stress or the change in surface stress, which has happened because of antigen antibody. We had a slide on bimetallic effect. There was a deflection, delta Z, because of a change in temperature, delta T. Forget about what is there present here. Just concentrate on alpha 1 and alpha 2. These are the temperature coefficients of expansion. If the two TCEs, temperature coefficients, are different, there will be a deflection. If not, this will be 0. So, if alpha 1 and alpha 2 are different and there is a deflection, then you know that there is a change in temperature. There has been an exothermic or an endothermic. This is important. Finally, resonant frequency changes. You can have a look at this frequency expression, and this is proportional to the root of the mass that has been absorbed. So if you know what is the change in frequency, you can measure that. Then you can determine how much is the magnitude of the adsorbed mass. Okay. So now what we have said is that because of certain reasons, the cantilever can deflect. Now, important thing is, how do you know that it has deflected? You need to monitor something, you need to measure something. Right? So one way is to do the optical technique, where you shine a laser on the tip of the cantilever, and that is collected by an array of photodiodes. And by knowing which diode has been fired, you can find out what is the deflection. However, since NanoSniff is more of an electrical engineer's company, we do something different. What we do is we use a technique of, it's an electrical measurement. We use the Wheatstone bridge configuration. We modify our cantilever. So we make our cantilever such that it is also having what is called as a piezoresistive layer. So this is the piezoresistive layer. There is a structural layer. On top of that, you have a piezo layer. On top of that, there is a immobilization layer. But there is a piezoresistive layer, so this is important. Now, if this cantilever bends, the piezoresistor is going to get strained, and because of the straining of the piezoresistor, its resistance will change. And using these contact pads, you connect it with your electronics, and then you can measure if there was a change in resistance, and if yes, then how much is the change in resistance. Okay. So I've talked about the geometry of the cantilevers, talked about some of the materials of the cantilever. But then you need to make the devices. Get the materials. So this is an example of a cluster tool which is used to deposit the materials with which the cantilever structures are made. For example, we need silicon nitride, that is deposited. We need polycrystalline silicon, that is deposited. We also need some sort of ammonia treatment, so that is also. This tool, which is a cluster tool, this I had designed for my PhD, and this is present at IIT Bombay, Nanofab Laboratory. The next thing, once you have deposited materials, you have got materials, then you try to do material investigation. So some of the investigations that we had carried out were FTIR, that you try to find out whether it is actually silicon nitride or not, using vibrational spectroscopy. You find out stuff like the density, the refractive index, and eventually what you also do is you fabricate the cantilever structure. So here what you see here, this is the cantilever structure, silicon nitride, hot wire CVD. And this was actually deposited on a silicon substrate, silicon wafer. So we had first patterned the silicon nitride in this shape and then removed the silicon underneath. So this is now a free hanging silicon nitride cantilever structure. You can see that it is not bent, it is straight. You can do certain experiments. Some more things that, I would say, characterizations. For example, you wish to find out what is the grain structure of your film, which is polycrystalline silicon. What is the density of that? Which is the crystal orientation that is dominant? How much crystalline it is? This was found out using Raman spectroscopy. The previous measurement done using XRD. You can also do a EFM. You can try to find the grain size from the surface, how much it is. You can also do electrical measurements, find from the 4 probe, find out its sheet resistance, etc. Okay. Just hold for a moment. Have a little bit of water. Okay. You would have, I believe, done lots of simulations. I saw that you have a NPMAS link. So maybe you have certain softwares like Coventer and IntelliSuite. So here are some simulations that we had done on micro cantilevers. Decade back actually, since it's a part of the PhD work at ToeQ. So what we had done is we first try to define what is the geometry, the size in terms of length, width, and thickness. We select materials, make it accordingly actually. Then we mesh this structure, and if you have done simulations, again you will know that the choice of the mesh is very important, because if you choose the mesh wrongly, then you could have incorrect results. And then finally you apply boundary conditions, and now you are fit to actually do your simulation. And when you say boundary conditions, you are essentially saying that some place you are going to apply force, some surface you are going to keep it fixed, some part you are going to apply a voltage, some part you are going to ground it, etc. So these are the boundary conditions. To the simulator, it is important that you supply the right material properties. Otherwise, it will be like garbage in and garbage out. Please be careful about that. And one good practice always is that you should tune your simulator, in the sense that whatever structure you have made, you need to check whether if it is giving you correct results or simple simple conditions. For example, you can do a paper calculation using already known formula and try to find out if that is similar to what the simulator is telling you. So that is called as tuning the simulator. So are you able to hear the rain? There is a heavy shower that is coming in. Here. So I'm in Mumbai, so it's rainy season here. Okay. Some of the simulations that I have done, here is an example. So let us say I apply a force in the negative z direction. Because of the application of force, how much is the deflection and how much is the change in resistance for a given deflection? So that the simulator can tell me. Then remember again the COVID example, antibody-antigen interaction. So this typically is a force which is stretching the membrane in the positive x direction. But because of this, there will be a deflection. It could be up or down. Now, because of the stretching and because of the negative x or the positive x deflection, what is the change in resistance? So now you can see that these are very interesting questions that the simulator can answer. So we found out some interesting results. Another thing that we did with the simulations was, okay, so if you, let us say, change the material properties. So we had, as I said, 3 layers, the structural layer, the piezoresistive layer, and the immobilization. Let us say you change the Young's modulus of one of these layers or all of these layers. Then what happens? Or let us say if you change the location of the piezoresistive layer, you could have it very near to the top surface, or you could move it very near to the bottom surface. What happens to the deflection and what happens to the change in resistance? These are some very interesting questions that you can answer. Okay. Then we did something more interesting. We found out using simulations what was the stiffness of our structure that we had intended to fabricate. So that stiffness was about 0.31 newtons per meter. Then we actually did fabrication runs. So I'm not aware of your background on fabricating MEMS devices, but very shortly and in a very superficial way, what I can only say is that we essentially we take a substrate, we add a material, we define the material or the geometry of the material that we want on the substrate. And then we remove or subtract the material that we don't want. And we then again clean. And then we repeat the process. So that is how you can see that we have deposited one layer upon the other and we have patterned it. And eventually we had SU8 cantilever. The SU8 cantilever, the substrate. These are the pictures. So this is the kind of what you see, edge on the edge, if you see something transparent, that is the polymer. This thing in light brown, this is the piezoresistor. Here are 2 cantilevers and here are the contact pads. Here is the entire die. So we did what is called as a stiffness measurement experiment. In this experiment, what we do is we deflect our cantilever with a standard cantilever, which is called as the AFM. Now you know the stiffness of the AFM cantilever. So these 2 cantilevers essentially they are forming a spring in series, and the situation is that it's similar to 2 capacitors in parallel, 2 resistors in parallel. So if you know the value of one resistance and if you know the total resistance, then you can find the value of the unknown resistance. So using the known value of the AFM cantilever per meter, you using this measurement, got certain curves, etc., etc. And finally, we extracted the value of the stiffness of the cantilevers that we fabricated, so which was about 0.25 newtons per meter, very close to 0.31 newtons. The measurement and the overall thing was seen to be all right. Then, as I had said, that cantilevers vibrate, so you can find the resonant frequency. Similarly, so we also did the same thing. We vibrated the cantilever in the AFM and found out its resonant frequency. Then one of my colleagues had made a very sensitive instrumentation. Using that instrumentation and using a setup, we had deflected our cantilever by known amounts, known distances. And we found out what was the change in resistance, the change in voltage, and change in resistance. So we could prove that our cantilevers are piezoresistive. So today, besides the polymer SU8 cantilevers that I talked about, we also fabricate cantilevers using silicon nitride, polysilicon. Here are some pictures. This, for example, is the transparent part is the nitride, and this brown part is the piezoresistive polysilicon. And the thickness is less than 1 micrometer, very, very thin. This is again the process. I will not get into that. Yeah. So fabricating a cantilever is quite a difficult job, I would say. First is, removing the substrate is a challenge, because you need to have the cantilever very thin, right? You need to remove the substrate. So removal is a challenge. First time, we didn't get the substrate removed. Second time, we had some black silicon was still lying around. Third time, we further reduced it, and eventually we managed to remove the entire silicon underneath, and these were free hanging structures. In cantilevers, another problem that we had faced was curling of the cantilevers. So this is like, the trunk of an elephant raised in the salutation form. This is because of the built-in stresses or the residual stresses in the thin films with which the cantilevers were made. So it's important that in the fabrication process itself, we introduce certain techniques by which you can kind of reduce the stresses. They might not become zero, but you can substantially reduce it. So we have that method with us. Okay. Now I come to the third part of the talk, which is the applications. We had made cantilevers. What is the reason for that? I talked about explosives detector. So we said, okay, can we detect explosives using these cantilevers? Now the problem with explosives is that they are very shy. You cannot, they don't reveal themselves. They have a low vapor pressure, so you cannot smell them. They have no smell or aroma of their own. And therefore, detecting them is a challenge for security. So what we said is, let us have cantilevers. So this is that these are those cantilevers. Let us coat it with a chemical which has an affinity for explosives. Here is a list of some of the coatings, say 4-MBA, 6-MNA, calixarenes, porphyrines, and stuff like that. And in the presence of the explosives, because of again the coating and because of the explosive molecules, there would be an interaction, there would be binding. Because of the binding, there would be bending, and we should be able to detect the bending with our electronics because of piezoresistive nature of the cantilever. So the cantilevers that we had fabricated earlier, and we had made a nice handheld device. So this device had a battery, it had all the electronics to monitor the resistance of the cantilever in real time. It also had a pump. It had a nice enclosure in which the cantilever. And then we switched on the pump and we did some suction and exposure measurements. So whenever we exposed it to TNT vapors or RDX vapors or PETN vapors, so this showed that the cantilevers were sensitive to exposure. However, there was a problem. The problem was that they were also sensitive to many other chemicals of daily use. For example, they were sensitive to shoe polish, to perfumes, to acetone, to the, what do you call it, agarbatti? I don't know what you call it in, what you call it in English. Yeah, I think they're called as incense sticks. So to those particles also they were sensitive. Now in a sensor, besides the sensitivity, selectivity is also a very important factor. We talk about that in the COVID case also. We know that the RT-PCR tests are sensitive and highly selective also. But the RAT tests, they are not selective. They have very poor selectivity. So similarly, in this application also, selectivity is important. So we said, okay, well, this will not work. So let us think of something else. So we shifted our focus, we shifted our technology, and we said, okay, we will use a different physics, different science. We will use micro heaters or micro hot. Now this is a nice cartoon, nice picture. This is the plate. This is the membrane, which is half millimeter by half millimeter. This size is half mm by half mm. So this zigzag, so this one is a platinum heater coil whose width is only 10 micrometers and thickness is 200 nanometers. And there is another platinum coil, you can see this. This acts as the temperature sensor. The idea is that because of heat the heater, apply a small voltage, heat it. And because of the heating, the temperature sensor to which you don't apply a voltage, but because of the heating of the membrane, the temperature sensor also will get heated. So its resistance will change. And using the TCR of the platinum coil, you can find out the change in temperature. What you can also see that in this scheme of things, you do an in situ measurement of the platinum and the microheater. So the microheater and the temperature sensor, they are in the same plane beside each other. You do a real-time measurement because as you increase the heater temperature, the same thing is sensed in real time by the temperature sensor. And you do an independent measurement. So the heater and the temperature sensor are different things. You don't use the heater itself to find its own temperature. So this is the beauty of the measurement. And on the left hand side, we have depicted the fabrication. But again, we will not get it. The idea is to use these microheaters and to use a physics of differential thermal analysis or deflagration to detect exposure. The deflagration is something like this, that if you give a rapid change to an explosive molecule, rapid change of temperature to a then it will explode. So what this heater is capable of doing is it can change its temperature from room temperature to 500 degrees Celsius in a few milliseconds. That is the rapid change I'm talking about. I will now show a video of the microheater. So this video was captured with a cell phone camera, and the voltage that was used to drive the microheater, that was a very low frequency sine wave that the camera could actually capture the heating. But otherwise, the temperature can go from room temperature to 400 degrees. a few milliseconds. You can see it once again. Okay. So what happens is that we have a nice chip, a cartridge of heaters, and we transfer the explosive. We collect out of a swab. We carry out deflagration. So if there is the explosive present, we get a signature which is something like this. If no explosives are present, we get a signature. However, things are never so black and white. There are also shades of gray. But then we have built in some very intelligent algorithms with the help of which we can determine whether whatever we have collected is explosive. Now this is our product. So this is nano sniffer, which is the explosive trace detector. It detects less than 10 nanograms of RDX, PT, and TNT. The time required is less than 10 seconds. And it purges itself, that is, cleans itself in less than 1 minute. The selectivity, so false positives are actually less than 2%. It weighs about 4 kg. You have visible and audible alarms. And we have, has been tested at even 55 degrees Celsius. So I'll again play a video. First, we go around the device. This is touchscreen display. The operator uses a swab. This is a blank swab. She will insert the swab in the instrument and she will run it. Since it's blank, there are no explosives. Message will come here in green color saying traces not in 8 seconds. That is the message. Now she will insert another swab which is having 10 nanograms of RDX. Again it will be run. And in again 8 seconds you will see a message here in red color now saying traces detected. And you will also hear a beep. I hope you heard the beep. In fact, I'll play it once again. Okay. Now, so let's say you develop a product. It is important that you do testing under international standards. So this is testing that we had done using the ASTM procedure for detecting for measuring and scoring the performance of explosive trace detector. So basically what the test says is that they divide the explosives into 8 classes like nitramines, nitroesters, peroxides, etc. And they have a certain background challenge material, which is the non-explosive. So it could be agricultural soil, it could be dust, it could be something that is collected from the exhaust of an automobile. These are examples. And eventually, you do certain tests, you do hundreds of tests actually for every type of explosive, and you find out, for how much times it failed, and what weights, at how much quantities it's failed, etc. And then you score. So we did that. It's very important to prepare the samples very properly. So I'll give an example how we had done the sample preparation. Since we need to measure 10 nanograms, we don't have a plain balance to measure 10 nanograms. What we essentially do is we weigh it in milligram range. Then we prepare a stock solution. So we know that I have 1.36 milligrams of RDX in 1 milliliter of solution. Once I know that, then I can take an appropriate quantity. Of course, you need to do mixing, so you need to shake it, etc. And then you can do serial dilution. So you can take something from the stock solution, let us say 10 microliters or 5 microliters using a micropipette, and you can put it in 1 milliliter of another solvent which is not having any. So you do serial dilution. Eventually, you will get a solution which will be having, let's say, 10 nanograms in one drop, and one drop is, in our case, 2.5. So that is how you quantify, and then you drop it on the swab that was shown, and you allow the solvent to evaporate, whatever is there in the swab, the residue, and then you can test. For false positives, besides the background challenge material, we tested with dozens of items of common use: water vapor, alcohol, perfume, deos, soaps, creams, shoe polish, toothpaste, betel nut powder, and tobacco, lots of this Vicks, naphthalene, camphor, etc. Okay. Now, when you sample any surface, the knowledge of the surface is also important, because it is not important, what is the material that is sticking. It is also the surface to which it is sticking. What explosive and what surface, and therefore what swab. So the swab material that we have also selected is based on the experiments that we had done with various surfaces. And there could be various reasons. We had done a testing. This is high temperature testing. We had tested it at 55 degrees Celsius. We had actually created a box. You can see here. Inside this, we had put our instrument, and using some bulbs and a couple of fans, small fans, and temperature sensors inserted inside. We did some temperature control, and then we tested our instrument. Here is field testing. So at IIT Bombay, the main gate, we had done a field testing, and this will give you an idea of how the instrument is used actually at security places. So that is it. Okay, so that's was I think the fourth part of my talk. Now to the last part. We are working on a project at Nanosmith to detect cardiac markers. So cardiac markers are certain proteins that are released in the blood after a person has a heart attack. Now, if you look at some statistics, cardiac diseases are a leading cause of death today in India, and many young people are affected. The other thing in cardiac event is that very difficult to detect, particularly in the early stage, because it's confused with general gas issues or something. Does not show up in ECG, and people or the doctors tend to make what is called as a delayed diagnosis, not in the golden hour, and because of which the damage to the heart muscle is done. So currently the way it is tested is the sample is drawn and it is sent to a pathology laboratory. And you can see that there is a huge time that is lost in transportation, particularly in a city like Mumbai or Chennai. Hours will be lost. And these tests for the cardiac markers are done in big laboratories. Small labs will not have the. So what we are looking for is an instrument that can be located at a clinician's workplace, the clinic, or at a small hospital, in even a semi-urban or a rural area. And the job of the instrument is to detect cardiac markers rapidly and in an inexpensive way. The cardiac markers of interest, they are, for example, myoglobin, CKMB, cardiac troponin, etc. So you can see that this A is the myoglobin, which is one of the earliest markers, comes out within an hour of the attack. Troponin is a late marker, but it's a very accurate marker. So to detect troponin in very small quantities is a challenge. High selectivity and high sensitivity, both. The principle that we employ is that we use microcantilevers. We use antigen-antibody interactions. Now here is something similar to what can be done for COVID also. So you essentially coat the probe molecule, is the antibody to the cardiac marker in which you are interested. And if troponin is present in the blood, there would be binding, there would be bending. This I have tried to show here because the antibody structure, this part is common for all antibodies. Only this part is the variable point. This part, this shape, this is what varies, and this is how it recognizes. This M is the antigen. Now we have developed certain techniques by which these antibodies can be coupled to the cantilever surface. We have also patented that technology. We have a US patent. Essentially, it is a process of attaching a silane molecule, then a linker molecule, then doing some sort of doing the attachment of the antibody molecule, then blocking, etc. That has been done. Of course, we are using piezoresistive cantilevers for the purpose. Initially, we did a lot of surface characterization, try to do with fluorescent antibodies, and try to determine if fluorescence is present, because that is the best of knowing whether antibody-antigen interaction happened. We also did some experiments with normal antibodies, IgG and anti-IgG. Those were also done. We could find out that the deflection actually happened. So that was very encouraging. And then we built up a setup, nice setup, using syringe pump, actually two syringes. One has the control, second has the troponin mixed in PPA. And here is the cantilever die, very small, and that is attached on a PCB. Wire bonding is done. And this is the electronics, which is monitoring the resistance of the cantilever. So you push PBS, that is the control and then you allow the cantilever to stabilize, and then you push in the analyte, which is having propellant. So what happens is depicted here, that it stabilizes, then you put in anti-IgG, and after some time, this anti-IgG reaches the cantilever where bending happens, because of which there is a change in resistance. So this is something that we have seen for whenever we have done an experiment. We have done this with IgG, we have done this with FABP, with myoglobin, with troponin. All times we have been successful. We have also made some instruments with which researchers like you can do experiments with microcantilevers. One example is an instrument called as OmniCan, which allows you to do what is called as headspace analysis. So basically, you take a vial and you try to heat it slightly, and you carry the. So this is the vial. You put some chemical inside, you heat it, and then you have a carrier gas. This takes the analyte vapors, okay, to the reaction chamber. So this is the reaction chamber. You can see here, and this is a flow cell inside which the cantilever die is present. And then you have the entire electronics to do the flow control and measuring the resistance of the cantilever. This is the OmniCan. It's a very nice device. So for example, here is a result. So when you, let's say, turn on acetone, you see a change in resistance. You turn off acetone, you again see a change. And lots of parameters can be varied. For example, the coating on the cantilever. DOC itself can be changed. The temperature of the mix cell, which is having the vial, that can be changed. Temperature of the sniff cell, I mean, cantilever is located, that can change. The flow rate of the carrier gas, that can. Lots of experiments, hundreds can be done. If you wish to play with the micro hot plates, then you have another instrument called as the Sensimer. So here you can attach. There is a attachment where you can put in the plug in the PCB, which is holding the micro heater, and you can measure the rise time, the fall time of the micro heater. You can give sine wave, square wave, triangular wave, any kind of wave. You can see how the response changes. So lots of again experiments can be done, and even more experiments. Interesting. We have made lots of new devices also, micro heaters with digitated electrodes. You can see here also. So these are the ID structures that we have made. These are 4 micro heater with IDs. These are actually used in the nano sniffer explosives. Okay, so I'm kind of concluding my talk now. So this is our team. Kapil, he looks after the business. He's also co-founder. Dipali, she looks after electronic systems and algorithms. Sachin, Dr. Sachin, he does the fabrication of devices. Rishikesh looks after the embedded system software. Nitin looks after the hardware, and Abhishek, he looks after the testing. So here is the last slide, I believe. So this is Pasteur's quadrant. This is from a book by Donald Stokes titled Pasteur's Quadrant: Basic Science and Technological Innovation. So it talks about knowledge creation versus knowledge utilization. And the 4 quadrants are: first is the teaching oriented research. Example is Sukrat. In his method, or in his philosophy, or in his way of work, knowledge creation and knowledge utilization were both low. The second example is of pure applied research. Example is Edison, Thomas Alva Edison. Knowledge utilization was huge, because he had done about thousands of experiments. He had found out the material for the electric bulb. but knowledge creation was not there. There was no new physics, no new knowledge that was created. Only utilization was there. And his competitor was Tesla. He used to say that, thousands of experiments that Edison did, I could have done it in about half a dozen experiments. Tesla was really a brilliant man. The third example is where knowledge creation is high, but the utilization is low. One example is Niels Bohr. That is pure basic research, finding the model of hydrogen atom, for example. That is Bohr's signature contribution. And there is the fourth thing, that is use-inspired basic research. Louis Pasteur is the example, where knowledge creation and utilization both are very high. And the example is, best example is pasteurization. Louis Pasteur observed that milk used to go bad after it was kept for several hours. After examining it under microscope, he could see bacteria because they were swimming around. He realized that those were organic matter. They had life in them because they were also replicating. And he realized that they could be killed by heat treatment. So now you can see that this is use-inspired basic research, and it is having both utilization, both creation, knowledge creation and utilization, because the entire world boils milk. So a path where applied goals are not inherently opposed with scientific creativity. And what essentially we try to do is we choose fundamentally new or novel phenomena, then uncover the basic science underlying it, and then translate that knowledge into an application. Okay. So at NanoSniff, besides work, we also have a lot of fun. Here is an example. I had shown NanoSniffer to you, and the operator actually operates a lever that has to be pushed down and it automatically comes. And that has to happen thousands of times during the life cycle of the product. So the spring that is present inside has to be highly reliable. Now we didn't want to test the spring by ourselves pushing it down hundreds of thousands of times. We said, okay, if we could do something like this. Is it visible? I'll play it again. Okay, so with that, I will be concluding. I'll be happy to take questions.
Thank you very much, sir. The session was very informative, starting from the introduction to the nanotechnology, scaling of the devices, fabrication, and the issues in design and fabrication of micro devices, and finally the applications, the explosive detections, and in biomedical application has been elaborated in detail. Now the session is left for the participants to raise their questions.
Participants, please you can raise your question. Any questions, participants?
Okay, so if there are no questions, there is no
Sir,
no issue. So
I have
my
understood your session. I think so.
so my email address is with the host, Professor
Okay, sir.
Kavita.
Okay, sir.
So if anybody is interested to know more,
Okay, sir.
please do drop in an email, and we'll be happy to get.
Okay, sure, sir. Sure, sir. So thank you so much, sir. You really
Oh.
your session is very informative, sir. Thank you so much.
Okay, welcome. Okay, bye bye. Take care.
Okay, sir. Bye, sir. Have a nice day. Thank you, sir. Hello, participants. Actually, yesterday feedback we will send you Zoom. Yesterday feedback as well as attendance plus feedback session, feedback form for this session we will send you Zoom. Otherwise, I will send it to your mail ID, register mail ID we will send it. Okay, now you can wind up. Tomorrow we will meet. Thank you, participants.